Thank you. No? All right, so I have the paper sign-in sheet. We'll do that at the end of class. If I forget, please remind me. So today we are continuing talking about linear algebra. We'll get to the intersections and calculating that stuff in the next class. Today, still just review about equations of lines and what we can understand about them. And then we'll look at an actual example of creating a cost and revenue equation for some particular scenario. I have to swipe that direction. So everything that we talked about last time, you can see on the left here. So just coordinates, we have an x, y pair in that order. Uniquely identifying a line, we can do with any 2 points or 1 point and a slope. That is enough. Point and slope, we usually would write like this. It's y equals mx plus b. That's how we calculate m. We'll do some practice with that. We had those special cases of perfectly horizontal or perfectly vertical lines where it just looks like y equals something or x equals something without the other variable. We talked about distance between 2 points. We'll use that again today. Lots of stuff about slopes and graphing lines as well. So parallel, perpendicular, coincidence, those are a big part of what we'll be working on today. I think I forgot to make a slide for it, but the preview question for next week is online. All the workshop content that will be this evening. I have the exact list of questions that we'll go through, so you can look at that in advance, try them before you come to the workshop. If you look at those and you think those are really easy, you don't need practice, then you don't need to come. Again, the workshops are in general optional. I'll talk more about that at the end of class, and then the homework assignment for the week 1 and 2 material together, that's also online. 3 people in this class have finished it already, so I think everyone's seen that. But we'll talk more about that at the end of class. All right. So let's see if we remember what we talked about last time. 3 simple questions here. See if you can solve these. All right, looks like we have a number of people finished. So let's do these ones. So remember, equation of a line, basic format is y equals m. B, m represents what?
The slope.
So m is slope and b is y-intercept. Right. So if we remember that, then they tell us the slope, they tell us the y-intercept. We don't even have to do any math here. We just write in the numbers. Second one, well, we have the first part of it, the slope given to us, y equals negative 1.5 x. But what about the other part? How do we figure out b?
We take the second one, b. It will be -1 anyways.
Okay, so people on, actually, I can't see if they're, yeah, who turns their microphones on. Bit awkward. Sorry. Try again. Okay, so this -1, -1. Remember, these are an x, y pair. So that's the x, that's the y. We just put those numbers in. So this plus some mystery b, and we have 1.5 times 1 plus b, and just some simple rearranging there. And what do we get?
Negative 2.5.
Negative 2.5. So our full equation here, y equals negative 1.5 x minus 2.5. So there's our equation. And the third one here. Okay. All right. Formula for slope, m equals delta y over delta x. 5 minus 4, the y's first. Remember, it doesn't matter which order we do these in, but let's call that one 1, that one 2. So 5 minus over 4 minus 1. So 1 over 3. Okay, so that's the slope. Remember, delta y is change in y, delta x is change in x. So we just subtract one from the other one and we get the difference. What's the distance between those two? And 1 second. So how we read this slope, remember, the number on the bottom is just saying if we take 3 steps with our x value along our x-axis, so it's positive. So 3 steps to the right means 1 step up with y. We'll look at some graphing examples a little bit later where we'll practice that. Okay, so now we have our slope. We have y equals 1 over 3 x, and then plus b, and we just use either of those 2 points, exactly what we did in the second part here. Let's use 1 and 4 here. So 4 equals 1 over 3 times 1 plus b. So b is equal to, okay, so 11 over 3, or 3 2/3, or 3.6 repeated. So whichever one we want. Then just put all that together. Y equals 1 over 3 x plus positive, yes, positive, plus 11 over 3. Okay, so that's what we practiced last time. Right. So last time we also talked about this vocabulary of what terms we use when we have sort of different relationships between lines. If we have two lines, they could just intersect in some spot, and it's not anything special about it. There's just some point of intersection. Or we could have this special type of intersection where it is exactly 90 degrees, or I think I maybe forgot to mention this, a right angle is specifically a 90-degree angle. So that is a perpendicular situation, perpendicular lines where they meet at exactly 90 degrees. Parallel where the two lines do what? They're parallel. What does parallel mean?
They
Okay,
never
no
meet.
intersection. They are always the same distance apart. They'll never cross each other. And last situation, coincidence. Okay, infinite number of intersection points because the equations might look different with different numbers, but when we draw them both on the graph, they turn into the exact same thing. We can't see any difference between the two. So those are the terms we will need. Nope. Should swipe the other way, right? This seems like I'm going backward. Okay, so we'll work on these questions here. We'll work on them one by one, do them together. So if we have some line, our same f of x from last time, and we have a point, how do we check if the point is on the line? And then here's, again, given f of x, how do we find all these different sort of related lines? What parts will be similar? What parts will be different from f of x? Very unintuitive. Okay, let's do the points on a line first. So our f of x, do we remember what the equation was from last class? Tell me. Don't look at, no. Don't look at your books. It's right here. Just look at the line and tell me. Not 2.5. Okay, so y equals -2, x plus 3. So we can see 3 as our intercept and then our slope of 2. So when x goes up by 1, right by 1, y goes down by 2. That's what this is representing here. Okay, so I have a point. Maybe it's on the line, maybe it isn't. This point is off of our graph. This point would be somewhere up about here. So I can't just look at the graph. How can I find this out? Okay, so again, this is this x, y pair. So if it is on the line, then I can put this x and this y in the equation here, and it should work out. All right, so let's try that. So we have 10 is equal to 2 times -4 plus 3. Now we can probably already see what's happening. 11. How do we interpret this result? Point is not on the line because 10 is not equal to 11. This is a contradiction. Fancy math word here. So it's a not true statement. So just quickly, I'll explain the kind of the logic behind this and why we're doing this. This comes up in harder questions as well. When we do this step right here and we substitute in the -410 into this equation, we are assuming the point is on the line, and then we're just doing some little simplification afterward. So we are already making the assumption that yes, it's on the line, but when we do our simplification, we say, no, wait, we have a problem here. Something doesn't work out. That's the contradiction. The earlier assumption is false, so it's not on the line. So that's kind of the logic behind what's happening here. So that's why the not equals here is actually meaning, no, it's not on the line. So if we want to test, just substitute in your points into the equation and see if both sides are still equal. All right, next. So we'll have a few different options here. And I keep erasing this. -2 x 3. So a few different options, but let's try to make a line that has the same y-intercept as our f of x here, but different slope. Okay, so first, what does opposite mean? And second, we have lots of choices here.
2x plus 3.
Okay, so let's look at this. The suggestion we heard. Y equals positive, so 2x plus 3. Intercept is the same, but our slope is different. So that will give us this one. This is not the only way to do this. Can someone give me a different line that has the same intercept, but a different slope? Zero, okay. So, sorry, x equals 0 or the coefficient is 0? I think you mean this part. All right, a different example, different equation, same intercept, different slope.
How about y equals to 3?
Okay, so we can do that. Y equals 3. What kind of slope is this? Flat. Just a perfectly horizontal line. It's going to look like this, and it's the same intercept here. So lots of choices here. If we change the slope, then we just rotate the line, but the intercept, the y-intercept, will sort of stay fixed. We have that anchor point, but the rest is sort of spinning around that point. All right, next, parallel. If we have two lines that are parallel, what will we notice about the equations?
Have the same slope.
Same slope, same slope. So a parallel line to our original one, f of x here, would be y equals -2x, and then plus any other value for our intercept here. So plus 5 or y equals -2x minus 2 or any other intercept. So let's draw these. That's -2x minus 2, and our pink one plus 5. Let's do here. Okay, it's not perfectly lined up, but close. So they'll be parallel. We can see that they do look parallel, but they have different intercepts. So we're just sort of sliding it up or sliding it down along our graph. Okay, so those are some simpler ways to change a line around. Next, perpendicular and coincidence. So again, with the f of x that we have here, how can we create a line that is perpendicular to that one? If two lines are perpendicular, what pattern or what relationship do we notice with them? Okay, but what about the equations of the two lines?
The slope is the negative.
Sorry, one second. Go ahead. Okay, if we multiply the slopes, they will turn into -1. Yes, so let's see what this would look like. I'll give a little more detail than that. So our original slope here is -2. Another way of writing this is -2 over 1. It doesn't change anything mathematically. So our other slope for our perpendicular line, what would it be in this case? 1 over 2. So what we are doing here is flipping over the fraction plus reversing the sign, whatever the sign is. And then, yes, if we multiplied these two together, it would turn into -1. But this is sort of the pattern. You flip over the fraction and change the sign. This is a negative reciprocal. Reciprocal sort of means like kind of like opposite, sort of like a matching pair of something. Yeah, -2 over 1. Yeah. So yeah, the pair here, this slope 2. The second slope is the negative reciprocal of the first slope, and in the other direction as well. So flip over the fraction, change the sign. That's the easier way to say it. So our slope, or our line here, y equals +1 over 2 x, and then plus whatever, just whatever intercept we want, just like we did last time. Let's say +2 or color y equals 1 over 2 x minus 3. Okay. So if we draw these lines, 3. Second one would look like that, and first one would look like that. So if it doesn't look perfectly perpendicular, then that's just because of my drawing. But that looks pretty close. That looks pretty close to 90 degrees, if not exactly 90 degrees. So there we can see the perpendicular relationship between the two. Okay, and our last one here. Again, -2x plus 3. Tell me the equation of a line that is coincident to this, but has different numbers. Not these same numbers here, but will still graph to turn into the same line. Are there no other choices? Is this the only way to create that line? Okay, so what are the other options? So for all the other things we were doing, the parallel perpendicular, we were just changing one side of the equation. To make a coincident one, we should be changing both sides. Okay.
How about 2y equals to -4x plus 6?
Good. I think you had it right. Can you just say it one more time?
2y equals to -4x plus 6.
2y equals -4x plus 6. So this is the same as this other one. We've just multiplied both sides by 2, but mathematically it's the same thing. So these could be rearranged. We could have it looking like this: 4x plus 2y equals 6. So we could have a form that looks like this, And then we say this other thing, y equals negative 2x plus 3. And we first think, well, those look like completely different lines. But then we just do some rearranging, simplifying, and then we realize, oh, wait, those are the exact same thing. Or we draw both of them on the graph and we realize they're perfectly overlapping and then they're coincident. So lots of different numbers that we could have that would still give the same thing. Just multiply both sides by the same whatever, or divide both sides by the same whatever, just scaling them up or down, but it will still turn into the same line. So coincident situations. So things that might look different at first could actually be the exact same line. Just do some simplification and you can check it. All right. Any questions? Right, and the last thing from the preview question that I gave you last week, shortest distance between A and this line f of x here. So let's see if we can solve this. Does anyone have an idea of what we could do, a strategy? Okay, what formula? And
A squared plus B squared is equal to C squared.
okay, so what we talked about last time, the A squared plus B squared equals C squared, Pythagorean theorem here, we used that to figure out the distance between A and B. And we said, let this one be side A, this one B, this one C. We had 4 squared plus 4 squared equals the other thing. And we simplified, worked it out. We figured out what C is. But this is a little different. This is kind of half of the puzzle, but we don't, what point will we use on f of x? We don't have a point yet to use the 2 points for this. Okay, there we go. Perpendicular line will be the shortest possible distance. That's the thing that we want to recognize here. So just quickly, intuitively, if I drew, let's say, a bunch of different lines between these points here, between the point and our f of x, so the one on the top is pretty long and we're getting shorter, shorter, shorter as we go. And also these angles here are slowly getting bigger. And eventually we would have a right angle, exactly 90 degrees, going through like this. So that is our shortest possible distance. We have a right angle there. So that is the points. So what we want basically is this coordinate right here. So we haven't yet talked about intersections of lines. So for today, let's just kind of cheat and say, well, it looks like 2, -1 on the graph. So there's our point, 2, -1. And then A here, we remember this was -2, -3. So there's the triangle. Call that A, call that B, and C. And then we can figure out our distance from that. So we could, again, figuring out length of side A here on the bottom. So -1 minus -3, or just count them off on the graph. It's 4 and the other one's 2. So 4 is the width there, and 4 squared plus height, 2 squared equals c squared. So we have 20 is c squared. So c is square root of 20. How can we simplify this?
14 plus 6. 16 plus.
Okay, so the 4 times 5, I'll write that in first. 4 times 5. Okay, I'll add one more step here. So square root 4 times square root 5. That's the exponent rules. Two things multiplied, we can split them up with our exponent and then simplify the one on the left. That's 2 root 5. So that's our length C. And yes, we could pull out our calculator and figure out exactly what root 5 is, but it's not a clean number. This looks nicer here. So that is our distance. So just distance between 2 points. And what point? We draw a perpendicular line and that intersection point. And we'll talk about the intersection points a bit more, or lots more, in our next class. Okay, I'll give you some more practice questions to do here. Given this line, y equals 3x minus 1, please find each of these 4 things relating to that line. No. Everything relative to this original line. The 4 questions are independent. Okay, that's been about 5 minutes. So we will go through this. So everything, yes, relative to the original line here, this y equals 3x minus 1. So a line that has the same y-intercept, but a slope of 6. Okay, so negative 6x minus 1. We just changed the slope. That's it. Second one, parallel goes through this point.
3x plus 16.
Okay, so give me the final answer first, and then we'll work through how we got it.
Y is equal to 3x plus 16.
3x plus 16. Okay, so to find this again, we have the same slope, the 3x, so y equals 3x plus some mystery b. Substitute in our values here. So we had 1 equals 3 times 5 plus b, and that'll be 15. Move that to the other side. That's 16, and that's it. That's our b value here. B equals 16. Perpendicular and goes through the point 10, 0.
Y is equal to minus.
Okay, so negative 1 over 3x
Plus b.
plus 10 over 3. All right, so this one perpendicular, our original slope is 3 over 1. So our perpendicular slope, second slope would be negative 1 over 3. Okay, there's our slope. So we have to go through this point. It's not just any y-intercept. We want through exactly this point. So if we substitute in those values here, then we have negative 1 over 3x, and here the x is 10, plus b, and then we'll have from this that b is equal to 10 over 3. Yeah, I know this, the writing looks really, really big for anyone online, but in the classroom here, it's kind of small. Okay, so there's our unique equation here. The last one, we actually have a few different choices, but someone give me one possible answer here.
2y is equal to 6x minus 2.
2x minus 2. Okay, so we have the same answer from 2 people. So, or we just multiply both sides by 10 or 57 or divide by whatever number. Just do the same thing on each side and we'll get a coincident line. So there are the 4 answers here, here, and our last one. Questions? Anyone? All right. All right, next part. We'll talk about different forms of equations of lines. So we had this one, which we've just been doing a lot with. This is the slope-intercept form because it tells us a slope and an intercept. It's very nice for graphing, very handy, but when we're doing just general algebra stuff, it's maybe not quite so useful. For other situations, we tend to have a different form, which is this one. So standard form, where we have all of our variables on one side and then the constant on the other side. So please note that we have different labels here. So we have this B and we have this B. And these two are not the same thing. We have a limited number of letters available to use. We have some overlap. So if we rearrange, we will get different numbers here. But if we take something in slope-intercept form, change it into standard form, probably all the numbers will be different in most cases. But when we graph it, we still get the same line. So the algebra looks different, but we still have the same basic representation of a relationship. So let's try here with y equals 3x over 3 plus 11 over 3. Let's change this into standard form. First here, what is the slope of this line? This is 1 over 3x. That's exactly what that's representing. So slope is 1 over 3. So if we change this into standard form, okay, so get rid of the fraction. Step number 1 for standard form is usually whole numbers only by convention. So no fractions. So multiply everything by 3. 3y equals x plus 11. Next step. Okay. Okay, so negative x plus 3y equals 11. So we want variables on the same side. So the variables to be together. And not always, but often we would change it so that the x value is positive, or whatever the first variable is, we want that one positive. And then if they're opposite signs, then we make the other one negative. So change this to be x minus 3y equals negative 11. So often we would go to that. By convention, that's usually how these would be written. It doesn't need to be. The really important part for standard form is that you have your variables together on one side, on the same side of the equation. That's and the constant on the other side. But typically when we see standard form, it will look like this. The x will be positive, and then the y will be maybe positive, maybe negative, depending on the relationship. Okay, and so we'll do the same thing here, but in the other direction. If we have something in standard form, we'll switch it over. If we want to graph that, if we want to graph that, two choices: change it to standard form and then graph that line, or there's a different kind of quick method of just finding the two intercepts, x and y intercepts. That's 2 points. We can draw the line from that as well quite quickly. So we'll look at both of those. Okay, so first we'll do switching this into into slope-intercept form. So what would we get? What's the first part? Go ahead. Okay, I'll just split it up into multiple steps just for clarity. So let's move the 5x over, so negative 2y equals negative 5x plus 4. And then we'll just divide both sides by negative 2 here. So y equals, we'll turn it positive 5 over 2x and minus 2. So there's our slope-intercept form. We can graph this pretty easily. There's our intercept right there, y-intercept. Our slope, again, the slope is telling us if we take 2 steps right with x, delta x on the bottom, delta y over delta x. If we take 2 steps right with x, then we take 5 steps up with y. So 1, 2, 1, 2, 3, 4, 5. That gives us that point here. We could do that again. 2, 3, 4, 5. Just barely off the graph. So we could do this in the other direction instead. So also, these could both be negative. It's the same thing. So 2 steps left and then 2, 3, 4, 5 steps down to here. And just draw the line between these points. So this looks like it's working. So the lower points plus the y-intercept, the line through that also lines up with the other point that we found. Looks like we did this correctly. So we're done there. So that is just converting into the slope-intercept form. So just some quick algebra, move things left and right. The other thing that we could do, our quicker method here, is just looking at this and quickly finding the x-intercepts and the y-intercepts. So okay, so we have the y-intercept. I know we found it here, but let's pretend we don't know that and we're just starting with this. What do we know about the x-intercept? Any x-intercept, what will always be true?
When y equals to 0.
Okay, that's the thing. Y will be 0. The coordinates, it's always x, comma, 0. We don't know the x, but it will always be 0. So this is a pair, right? These are coordinates here. So we can use this and say for our equation, well, 5x, don't know what x is, but minus 2 times 0 equals 4. So 5x equals 4. X equals 4 over 5. That's the x-intercept. And we can do the same thing for the y-intercept. So y-intercept is always the pair, will be a pair 0, y. So that gives us 5 times 0 minus 2y equals 4. So negative 2y equals 4, y equals negative 2. So there we can see the intercepts. So I know I wrote a bunch of stuff here, but when you're doing this, it can actually be pretty quick. So if we just look at the standard form here, what's the x-intercept? X-intercept means y is 0. So just forget that part. 5x equals 4. You can just do this in your head. 4 divided by 5. Done. We don't even need to write anything. We can just look at it and immediately see what the x-intercept is. Same thing for y. So y just means forget the x. 4 divided by negative 2, that's the y-intercept. So 2 points, very quickly, we can draw the line from that. So that's a nice shortcut for the standard form. Instead of having to convert into slope-intercept form, we can just very quickly find both intercepts. When we do our linear programming thing in week 5, we're going to use that method to save us a lot of time. So useful to remember that one as well. Okay, so convert to slope-intercept form, or do this shortcut and just find the two intercepts and graph based on that. Good questions? All right. So last bit for today, we'll talk about costs, revenue, profits. So we'll review the terms that we had last time, and then I will show you some, or we'll look at an actual example. So we talked about this, the costs. What exactly do we mean by cost? Cost to who? Right, production cost. So the people making the product. Cost to customer is price. And so revenue is the price times the quantity sold. That's money coming in to us. Profit is revenue minus cost. So again, if we want to be technical, this is gross profit. I'll review this part again. Costs, we split up into these two parts here. Fixed costs, which are not dependent on quantity sold, and then variable costs, which are dependent on quantity sold in particular, not dependent on other things, specifically on quantity sold. So fixed costs are just a number, some constant. Variable costs will be your quantity sold, Q, times the cost of producing one item. For the simple situations we'll look at to start, we'll assume that the cost per item is just a fixed value, and then we'll look at what happens when it changes later when we get to our calculus stuff. So total cost, quantity sold times cost per item, variable costs plus fixed costs. There we go. Second part, total revenue. I mentioned this already. P times Q, price that the customer pays times quantity sold. Remember, price is constant. Generally speaking, if 5 people walk into my store and buy the same product, I don't charge them 5 different prices. They pay the same price. Price could change in the long run over like a few months or something, but at least in the short term, prices are constant. So TR, total revenue, price times quantity, and profits, revenue minus cost, TR minus TC. And we have PR here, price times Q, or P times Q, price times quantity, and then subtract from that the total costs. And that will turn into something that we can graph as a straight line of an MX plus B, or I guess minus B, because we're always subtracting the fixed costs. But it's the same basic style. We can represent this with a straight line. So let's actually look at an example. So this is some information about the iPhone 6. I know this is an older one. It's ancient now, but Apple does not really make these numbers available easily. So this is one where like I was able to actually find good data on it. So older iPhone 6, the device sold, at least the US price when it was brand new, $649. But what always happens, companies will just, the older one, and they'll take it apart and look at all the components. Oh, we can order this thing from this company, and then here's the manufacturing cost, and they'll say, here's the actual production cost for one of these things. And they estimated it at $200.10. So quite different from the actual sale price here. But let's try to just break down the situation with a cost, revenue, and profit equation here. So first, cost. Total cost. We have variable cost plus fixed cost. The variable costs are $200. Let's just say 200 for simplicity. 200 Q plus fixed costs. So fixed costs are basically, in this case, development costs, sort of like designing the new phone, making whatever changes from the iPhone 5. Apple does not release this information at all, but let's just take kind of an educated guess. So they release sort of a new model to the phone every year. And so it's about, let's say they spent a year developing this phone, and people who work in Silicon Valley in the US, where Apple's headquarters are, they'll earn on average about $100,000 per year. That's their salary. And Apple has lots of people. So let's just take a guess or rough estimate and say they had 1,000 people working on this. So 1,000 people working for 1 year. So 1,000 times 1 year's salary, that's a rough fixed cost here. So $100 million for sort of development costs. Okay, so 200 Q plus 100 million. Revenue, what is our revenue equation here? Revenue.
$649 for each car.
So we want it as a variable. I looked up the actual sale numbers. I'll tell that to you in a moment. But for right now, we don't actually care about the sale values. We're imagining this is like a, before we actually make the product, can we make money? Should we start creating this product? So let's just call it 650, easier number, times Q. That's our total revenue. So the profit equation, if we were to write that out, it would be, I'm not going to write that out here for sake of time, but total revenue minus total cost. So 650 minus 200 Q. So 400, or I won't write the whole thing, but we'll just write the final version. Profit would be 450 Q, then minus the fixed cost. So 100 million. So each of these things, straight lines, we can put them on a graph and look at them. What we care about here is the relationship between cost and revenue. Where do those two lines intersect? So I have, or I'm going to show you here a little digital demonstration. This website you might know about, the algebra. It's just basically a online graphing calculator. I had here. Normally we would have to zoom in, or we would start very zoomed in here. Quite small numbers. Last class, just rewrite it. So we'll write total revenue first. Total revenue. This website doesn't handle like Q's or P's, so we just have to write it with the Y and X. But the Y equals 650Q, which we'll write as X. There's our line, and total. Let's switch this to green. Sure. And our total cost, which was Y equals 200Q, so X, and then minus, we estimated 100 million. Yes, you're right. Profit. Thank you. Okay, so we can't see the total cost line because, well, it's huge. Those are really high costs. So we have to zoom way out here. So what we care about is this point here where these two lines are crossing. So this point of intersection is the break-even point. break-even point because it's where, for this product, where the company breaks even. If their Q, their quantity sold, is less than that point, and let's zoom in so we can see the number here. You can see on the bottom. So Q is, again, our independent variable. That's our horizontal axis here. And then dollars is the vertical axis here. So if the Q value is less than that amount, then they haven't sold enough and they have an overall loss with this product. So if this is the analysis they're doing before they release the product, they say, we can't sell enough to make money. We're not going to do this one. If their Q value is above that point, then they say, okay, we can make money. This is a good idea. Let's actually make this product. What is the Q value approximately? You can just read it off the bottom there.
Around 220,000.
So about 220,000 units. So they have to sell about, again, we've made some guesses here, but about 220,000 units in order to make money. What do you think? Do you think Apple made money off the iPhone 6 or not?
Yeah, they did.
We say yes. Okay. So I looked up the sales data. Again, 220,000 is the amount that they needed. Type this here. All right. So 220,000. For this product, the iPhone 6 was on sale for 4 years total after its release from 2014 to 2018. Apple sold 4 million units in the first day. In the first weekend, it was 13 million units. And lifetime sales over the 4 years was actually 220 million units. So they needed, again, we've made some estimates, but 220,000, they sold 220 million. Yes, they made a lot of money on this product. This was around the time that they built that brand new headquarters, that really big circular building. You might have seen the photos. That building that cost like at least $2 billion to build. That's a lot of your money that they used to build that. Yeah, so I have a Samsung phone. Samsung also built like a big fancy headquarters in Silicon Valley, so they have my money. So we're all kind of idiots, like giving these companies way, way more money than what the products actually cost. But that's the basic breakdown here. I've made a lot of simplifications. They also have to pay for the marketing, and they have their teams of lawyers and admin costs. So it's not net profits, but gross profit is gigantic. That's why they keep making new phones every year, and everyone keeps buying them. Okay. So for our next class, we'll look at a simpler business sort of scenario, one where we don't have so many complicated things to guess about. So we'll look at that next time. Again, the main idea here is this break-even point. We're going to talk about that a lot next week. So where is the point where you switch from losing money to earning money overall? And then can you actually sell that much? All right, so I still have some stuff to talk about to wrap up. Review here. So basic cost, revenue, profit equations. With the Apple example, we've made those. We can switch between slope-intercept form and the standard form. We figured out how to find if a point is on a line. It's a quick test. We just substitute it in the values. And also, if we have one line, then we can find related lines. Oh, here's a parallel one. Here's a perpendicular one. Here's a coincident one. All right. So the review, if you want to do some more reading about this stuff, if some of these concepts are confusing for you, these are the parts of the textbook. These are some general practice questions that I recommend. And again, if you look at the list of questions for the workshop, there's like an exact, like these particular ones would be good for you to practice. So workshop, all of the workshops will be from 7:30 to 9:30. That's a permanent time change because we had time conflicts with the other ones. All online because you don't want to stay here until 9:30 every night. Like we have this class first thing in the morning. I don't want to stay here for 12 hours every day either. So online, register through the My SolBridge page. Attendance, as I said, it's optional for most people. I emailed a few people this morning, and based on your sort of math diagnostic test scores and then some other stuff, I sort of identified some people who could benefit from some extra help. So those people will be very strongly encouraged to attend at least a certain number of workshops. So if you got that email from me, then that's you. In the future workshops, I do plan to have kind of half the time being just sort of a easier review and then half the time with some more challenging questions. This week, it's going to be sort of a slower pace, maybe for people who've just never seen this linear algebra or completely forgot about it. So if the stuff that we did today or the questions listed for the workshop are really easy for you, then okay, you already know it, that's great. This workshop's going to be more for the people who need a bit more help on this stuff, okay? Right, preview question for next week. 2 more things to talk about. So preview question, they're here. It's listed on the classroom page already. You can see them about intersections of lines. The kind of big thing to talk about here, the homework assignments. So for the week 1 and 2 content, the homework question is up. Again, a few of you have done it already. So it's these 4 parts here, these 4 questions. These are from the textbook. The textbook, I put a link to this, everything on the classroom page. You can find it there. This is a more traditional style homework assignment. So you're writing it all out by hand. It's going to be graded. If you have mistakes, you're going to lose points for those mistakes. It's written by hand. You are going to scan this, scan your, not just a photo, but use an actual scanning app to make a nice, clean PDF of your writing. And that's what you are uploading. I'll have a bit more details about that in a second. So due on Sunday, same time as the preview homework at 8 p.m. Okay, 2 more slides about this. There are often problems with the writing homework, so I just want to say this once very clearly, and then hopefully it won't happen anymore. So written work, please write cleanly and just in a way that's easy for anyone to read. So like if you can't read it or like actually look at your images, or if it's really hard to read, we're just not going to. Way too many students. It already takes us a long time to do the grading. If we have to spend twice as much time just on your work because your handwriting is bad, we're just not going to. So best practices here, because you're scanning, use a thick pen or maybe a thin marker. I used a thin marker when I wrote these ones. Write the question number really large so we can see where your work starts. Underline or circle your final answer so we can see where that part finishes. Leave some white space between your writing. Don't pack everything in really tight. Please have your name and student number on it. Okay, and scanning apps, those are really important here. It takes multiple pages and combines them into one file. It shrinks down the file size. So instead of like 10 gigabytes of data from all of your like giant files that your phone takes, it's just a very simple compressed file. It's a lot quicker for me. Scanning apps, there are lots of them. There are lots of bad ones, but there are a bunch of good ones as well. So Adobe Scan is great. The Microsoft Lens, these are all free, also works very well. Google Drive has a scanner thing built in. Also the Google Classroom app. So for this assignment, when you press the like attach files, there'll be a like you can upload a file, or just on the right, there's an option scanner that's built into the app. It's really quick to use. So I know a bunch of students would like they take a photo and email it to themselves, and then on the laptop they upload it to some other website and combine it, and then like it just, I don't know why they spend like 20 minutes doing this. The scanning app will take like a minute. It's really quick and easy. So please actually do that. I even posted a video. On our classroom page, screen work for homework. So at the bottom here, this is what the work should look like. And tips. And a video of me using these 4 different scanning apps. Again, very quick. So if you tell me, oh, I don't know how to use them, it's too hard, I'm not going to accept that. Like I scanned 2 pages. It took me 2 minutes, and I was even like verbally explaining what I was doing at the time. So it really is not hard. Please just take the 5 minutes it takes to learn how to do this. The other thing that lots of people forget is you upload the files, and then there's a button that says submit. Yes, it's the right files. Yes, I'm ready, and actually submit. You need to do that. That's when it creates a timestamp, and that's when I know you've submitted your work. So if you don't press the submit button, I don't see that your work is ready. There's no time. I don't know when you finished it or when you uploaded it. So that's not enough. You have to actually press that submit button. It's a big button on the app. It's very hard to miss, but just actually remember to do that, please. Okay. I think it's mostly common sense, but just some people get confused about this stuff. So just please make sure your work is uploaded properly. It's easy to read. It's nicely scanned and everything. Okay. Any questions? All right. So then we are finished. I will maybe see you this evening for the workshop. And if not, I'll see you on Tuesday. The sign-in paper is up here. So please sign before you leave.